Welcome to the Inspiring Tech Leaders podcast with me, Dave Roberts. Today I'm talking about something that doesn't receive nearly as much attention as the latest AI model releases. Instead, I'm going to talk about compute. More specifically, we're asking a question that every technology leader should now be asking. Is AI becoming too expensive to scale? It is very possible that the future of AI won't be won by whoever builds the smartest models, but by whoever makes the inference dramatically cheaper. An interview with Nvidia's Vice President of Applied Deep Learning contains one of the most surprising statements I've heard this year. He openly admits that the compute costs for AI are currently higher than employing the people. This means that the industry may actually be building the wrong AI infrastructure altogether, chasing bigger GPU clusters rather than smarter architectures. Taken together, these pieces suggest something extremely important. The next AI revolution won't be about intelligence. It will be about economics. Today I'm going to explore why inference has become so important, why today's AI business models may be fundamentally unstable, why enterprises are beginning to question return on investment, and what technology leaders should actually do over the next few years. So let's dive into it. For the past 3 years, we've lived through what many people have called the AI arms race. Every other week seems to bring another larger model, another record-breaking benchmark, another announcement of billions of dollars being invested into data centers, GPUs, and specialized chips. The conversation has focused almost entirely on capability. Which models writes the best code? Which chatbot reasons more effectively? Which image generator creates the most realistic pictures? Yet capability has distracted us from the equally important question: how much does this actually cost every time someone presses enter? Recent research argues that training is no longer the dominant economic challenge. Instead, inference has become the real cost center. Training a model might happen once every few months, but inference happens every single second of every single day. Every chatbot conversation, every AI-generated report, every coding assistant suggestion, and every document summary requires inference. Even if each request only costs fractions of a cent, billions of requests quickly become enormous operating expenses. The cost per token and energy per token are becoming the defining measures of AI economics. The companies that succeed may therefore be those that reduce the cost of every interaction rather than simply increasing model intelligence. This is an important change in perspective. Imagine two AI models that achieved almost identical performance. One costs 10 times less to operate than the other one. So which becomes the commercial winner? History suggests cheaper technology usually wins. Think about cloud computing. Think about broadband internet. Think about smartphones. Cost eventually drives mass adoption. Combining several technology improvements could eventually reduce inference costs by as much as 100 times. If that happens, AI suddenly becomes viable for thousands of business processes that currently don't make financial sense. Many organizations have been operating under the belief that AI automatically reduces labor costs. The reality appears considerably more complicated. Replacing human effort with AI doesn't eliminate costs. It replaces salary costs with compute costs. Those compute costs include GPUs, networking, electricity, cooling, cloud services, storage, inference APIs, security, orchestration software, observability tools, and increasingly sophisticated infrastructure engineering. In many cases, organizations are discovering that while headcount may reduce slightly, infrastructure spending increases dramatically. The result is not necessarily lower costs. Instead, costs move from human resources to information technology. This shouldn't actually surprise us. Enterprise AI isn't just running a chatbot. Behind every intelligent assistant sits an enormous technology stack. Multiple GPU servers, massive quantities of high bandwidth memory, ultra-fast networking, distributed storage, specialized software layers, security monitoring, power infrastructure, cooling systems, redundant data centers, and increasingly complex orchestration software. The end user sees a simple conversation. The infrastructure team sees an incredibly expensive distributed computing platform. The industry has become obsessed with adding more GPUs rather than questioning whether today's architecture is fundamentally the right approach. That argument deserves serious consideration. Historically, technology advances haven't simply come from scaling existing systems. They've come from challenging the architecture. We didn't make aeroplanes dramatically faster by simply adding more engines. We redesigned wings. We didn't make databases infinitely scalable by buying larger servers. We redesigned distributed systems. The same principle may now apply to AI. Research also suggests that reducing cost per token also reduces energy per token. These two metrics move together. This matters because power is rapidly becoming one of the biggest constraints on AI expansion. Data centers are consuming extraordinary amounts of electricity. Grid capacity is becoming a limiting factor. Power availability is delaying new facilities. Cooling costs continue to rise, and governments are increasingly questioning environmental impacts. Suddenly, efficiency simply isn't about saving money. It's about making AI physically deployable. If you can't access enough electricity, it doesn't matter how powerful your GPUs are, you simply can't scale. This creates an interesting contrast with the AI headlines we normally see. The media focuses on larger models. Infrastructure leaders increasingly focus on smaller electricity bills. These are two different conversations. One is about capability, the other is about sustainability. Technology leaders should pay attention to the second conversation. General-purpose GPUs transformed AI because they were flexible enough to support many different workloads. However, flexibility often comes at the expense of efficiency. Today's GPU market is incredibly concentrated. Tomorrow's inference market may become much more diverse. We may see specialist chips designed for healthcare, specialist chips for financial services, robotics, edge computing. Specialization could become the next competitive advantage. But infrastructure isn't only about hardware. Software optimization may actually deliver even larger improvements. Model pruning, better orchestration, intelligent batching, context optimization, memory management. These techniques often reduce computational demand without noticeably affecting output quality. In other words, software engineering becomes just as important as semiconductor engineering. That's an encouraging message because software improvements are genuinely faster, cheaper, and easier to deploy than replacing an entire fleet of data center hardware. Now, let's step back and think about enterprise adoption. Many organizations remain stuck in pilot mode. They've successfully demonstrated AI. They've impressed senior executives. Employees enjoy using chatbots. Developers like coding assistants. Customer service teams experiment with AI agents. Everything appears positive. Then finance becomes involved. Monthly AI invoices start arriving. Cloud spending increases. GPU utilization remains surprisingly low. Suddenly the questions change. Not can we use AI? Instead, can we afford to use AI everywhere? That's a much harder question. Recent reports suggest many enterprises are struggling with unpredictable AI operating costs, prompting organizations to introduce FinOps-style governance, usage monitoring, and stronger controls around token consumption rather than allowing unrestricted experimentation. This leads us to one of the most important leadership lessons. AI should no longer be viewed purely as a technology project. It has become a financial management challenge. Technology leaders need visibility, they need governance, they need optimization, they need business cases, they need cost allocation, and return on investment measurements. Without those capabilities, AI spending can expand faster than business value. That's exactly the warning several industry observers are now making. Companies that succeed won't necessarily spend the most, they'll spend the smartest. There's another misconception worth addressing. Many people assume AI costs naturally decrease over time. Historically, that has often been true. Cloud storage became cheaper, network bandwidth became cheaper, computing power became cheaper. However, AI demand is increasing almost as quickly as efficiency improves. Every time inference becomes less expensive, developers create more ambitious applications. Cheaper AI encourages more AI use. Economists call this the rebound effect. Lower costs stimulate higher demand, so even if individual AI requests become cheaper, total infrastructure spending may continue increasing. That's why reducing costs alone isn't enough. Architecture, governance, and business priorities all matter. One of the most interesting debates emerging today concerns whether enterprises should always use the largest model available. The answer increasingly appears to be no. Smaller models often deliver excellent results for narrowly defined business tasks. Local inference can eliminate cloud costs. Hybrid architecture reduces latency. Task-specific AI frequently outperforms enormous general-purpose systems within specialized domains. This represents a more mature approach. Rather than asking which model is smartest, organizations begin asking which model is good enough. That question could save millions. As we look towards the next decade, I believe we'll witness a significant shift in competitive advantage. Today's winners are companies building larger models. Tomorrow's winners may be companies delivering similar intelligence at dramatically lower cost. Think back to personal computing. Eventually, every manufacturer built reasonably powerful computers. Competition shifted towards efficiency, usability, and affordability. AI appears to be following a similar path. Eventually, intelligence becomes commoditized. Economics becomes differentiating. So, what should technology leaders do? First, stop measuring AI success purely through accuracy. Measure cost per business outcome. Second, understand your inference costs in detail. Third, explore smaller models before automatically deploying the largest available foundation model. Fourth, invest in optimization skills alongside data science capabilities. Fifth, prepare for rapid changes in AI hardware because today's infrastructure decisions may look very different within 3 years. And finally, remember that sustainable AI adoption depends just as much on financial discipline as technological innovation. The companies that master both will have considerable competitive advantage. Today's discussion reminds us that AI isn't simply about creating more intelligent systems, it's about creating economically viable systems. The next breakthrough may not come from another trillion parameter model. It may come from a chip, an algorithm, or an architecture innovation that makes today's models 100 times cheaper to run. If that happens, AI adoption could accelerate beyond anything we've seen so far. That's why compute deserves as much attention as intelligence. Because without compute, intelligence alone cannot scale. Well, that's all for today. Thanks for tuning into the Inspiring Tech Leaders podcast. If you've enjoyed this episode, don't forget to subscribe, leave a review, and share it with your network. You can find more insights, show notes, and resources at www.inspiringtechleaders.com. Head over to the social media channels. You can find Inspiring Tech Leaders on X, Instagram, Inspo, and TikTok. And let me know your thoughts on AI compute costs. Thanks for listening, and until next time, stay curious, stay connected, and keep pushing the boundaries of what's possible in tech.